Ooh, oh, please don't. No.
Sorry, I'm backtracking. Question about the angle, negative 51.3. You said it was below the positive axis, but theta minus is like up.
Theta negative is just this angle right here,
Right.
but the vector itself, when I'm trying to identify the direction of the vector, it's going down in that direction.
Okay.
So 0 degrees, negative angles go.
Oh, I see. Because I'm seeing like theta negative next to, yeah, right there. So
Yeah.
I was thinking like it's positive, but yeah.
Yeah, and that is a positive number, it's just
That was
when I put it into polar form, I need to differentiate between that angle and that angle.
Okay, thank you.
So we need to break them each into components.
That's where I was heading. And that, I still believe that's easier than law of cosines, law of sines, but if you like the other method, more power to you. All right, I've established a convention here. So 13911.8 cosine of 21 degrees, I hat, plus 1391.8 cosine of 21 degrees, j hat, plus 658 5.4 cosine negative 51.3 degrees. Do any of you know of any classroom on this campus where the boards can be raised?
Not the whiteboard.
I had plus 658.5.4 sine of negative 51.3 degrees j hat. And then somebody's going to work through the answer and tell me. And while you're doing this, just want to throw out there that there's going to be a lab next week or the week after, probably next week, where part of the analysis is you're going to have to do something similar to this. The plus and minuses might be reversed, but there's also a traditional wrong way that some students will do, and I hesitate to show it to you because I don't want you to get stuck in your head, but if you think it would benefit you to see the way not to do it, I will gladly show it to you. Does someone have an answer? Brooke, what do you have?
Yes, 2075.5.
2075.5.
And the units are,
Is that the final magnitude? Or is that just the I hat direction or the j hat direction, or did you just add everything?
oh, why did I add them together? Sorry. Let's see. The I hat direction. Sorry, 1 second. I added the wrong thing, so I'm gonna change this.
All right, back to the drawing board.
want us to go ahead and add together, like, the I-hats and the J-hats?
No, just want the I-hat, the J-hat.
What?
So I want the I-hat part and the J-hat part. Alright. Yep. So are you about to tell me just that, or are you about to tell me the sum of the I-hats?
I was gonna tell you the sum of those.
Okay, go for it.
I don't have it yet.
Oh.
Sorry. Sorry.
I have 5,416
5,416.
Newton coulombs I-hat, Newton per coulomb,
Okay.
correct, minus 4,640.7 newtons per coulomb J-hat,
4,640.7.
0.7 newtons per coulomb J-hat.
Okay. And for whatever bizarre reason, I put the I-hat and J-hat up front instead of at the end. Anyone else get those same numbers? Okay.
I got the I-hat one.
So would you call this the net electric field at point P?
Yes.
Is that what it is?
Yes. So from a notation point of view, this could also be written as 5416 I hat minus 4640.7 J hat, parentheses around the whole thing, and then newtons per coulomb. So, which everyone works for you. Don't put, if you're only going to put units once, you do need the parentheses. Let's see if this actually makes any sense whatsoever. Our two magnitudes were a little over 6,500 and then a little under 1,400. So one of them is roughly 5 times larger than the other one, very crudely. So I have one of the vectors going at a 21-degree angle. That's roughly 45, so 21-degree angle like that. And the other one is at a 51-degree angle, so, and it is 5 times longer. And I'm gonna make that shorter so that it's easier. So it's 1, 2, 3, 4, so, and then 5. It's a crude sketch, and even cruder by the way I've done it. Adding 2 vectors at the tail. Those are supposed to be parallel, and my resultant is right there. Or I'm practically going to the right just as much as I'm going down. Not down quite as much, but so if that's roughly 6,500 or something, 5,500 would be roughly to there, so basically going out to here, and then down not quite as far as I went out, which put us somewhere around there. So it feels right that that answer makes some sense based on what we had already. This method right here is from straight up I hat J hat, or here I hat J hat addition, and this one right here is, well, in essence, the way you would set it up if you were using law of sines, law of cosines for those fans. And I think that's about all I can really say about this one. It's as exciting as it seems. And you can pretty much be guaranteed that you're going to have to do this at least 2 times after this, where you get a grade on it. this space over here. And I'll find out what we're there. All right, so let's sort of, oh, I guess one other thing to look at. So the final electric field is not pointing in this direction or in that direction, in either direction that those two black lines are showing, but it is pointing basically at the sum. And you can do that for almost any point on here where you can figure out what the size of the two lines are, figure out what the direction is. Another way of doing it, just a quick and dirty way of doing it, is if I've got a plus and a negative, or plus and plus, whichever way you want to do it. If you think about the plus sign as like a water fountain, and it's spewing water outwards. The negative sign you can treat like a drain. So if I have two positive charges here, and they're just sort of spewing this electric field out in all directions, ultimately, what we're going to end up with is it's going to cancel out here. Anywhere else it meets, as the water is shooting this way, it's going to sort of bounce off of each other. And so what we'll end up with is a fading marker. These should curve more. And then there's symmetry. I lost where it was. And then there's a symmetry. And that is incredibly badly drawn. And then flip over here. If I had a negative there, which is easier to draw, I got plus and minus. Basically, I'm going to have anything shot to the right is going to go straight into the drain. Anything that's shot this way is eventually going to get curved into the drain. And that's basically what the electric field lines would look like. If I take a point anywhere on the curve, assuming that my curves were correct, if I wanted to find the electric field at that point, well, my electric field goes from positive to negative, so it's going, so the electric field lines goes like this. At that point right there, if I calculated the electric field, it would be tangent to the curve. So if that's point P, that is the electric field at point P. If I try to figure out the electric field at that point, well, it's going to be going closer to straight down. So one of the rules for electric field, it's going away from positive towards negative. So away from positive toward negative. It is tangent to the curve, to the electric field curve. When you draw the field lines, despite the way I drew it right here, and I'm just sort of embarrassed by that. Good thing no one's recording this. The electric field lines do not cross. So when you do the sum of the electric field from the whatever your charge distribution is, at any point, eventually you'll end up with a nice smooth. You should end up with some sort of curve there, but the two curves are not going to intersect. You will not get, the way I had drawn it there, you will not get an electric field line going like that. And in the end, after doing the sum of the electric field, you will not get this. This is, you know. And the last one I think you can probably pull it from what I've drawn here. But if I'm drawing electric field lines from one charge to the other, and I draw a circle, and then I draw another circle here, if those circles are the same size, which circle has more lines going through it?
The one to the left.
And that would indicate a stronger electric field. So we can indicate strength of an electric field by either the number of lines that go through a particular area, or the classic method, instead of drawing this nice smooth curve, draw a whole bunch of line segments. So if I had a positive charge here, you know, a steadily decreasing length of line, or just draw them as a solid line right there and look at the concentration of lines in the circle. This is not to mean that, oh, if I only draw 4 lines, then it's the same electric field no matter what, because my circle, it doesn't work that way. No matter how many lines I draw, the higher concentration of lines in a circle means a larger electric field strength. And so that would be sort of another bit here. Electric field lines per area is proportional to the electric field strength. Questions before I erase more? I guess we have the answer there already.
Just to clarify, you're using that greater than symbol to indicate the electric field? Is that what that
Greater
means?
than,
Maybe
oh,
I'm
oh,
just reading it.
that right there, those are like burger dots. The
You just
bullet points.
Oh,
Yeah.
got it, thank you.
Yep. You know, I should get used to saying bullet points, because that's what I called them before I started working with this guy who kept calling them burger dots. It was named after some guy named Berger who was advocating back in the 60s or 70s the advantage of using what are now called bullet points. Other questions? All right, let's think about, I've got a surface here. I have a conductor. And I magically put a whole bunch of electrons all over the surface. It's supposed to be a square. So I take an even distribution of charges and I put them all along the edge right there, and then I step away. What is going to happen to those charges?
It should stay constant, right?
Why?
Because it's a conductor,
Therefore,
like transfer of charge it conducts the charges.
conductor, the electrons can move easily. I'm assuming that I somehow set it up and I step away. The charges, the number of charges on that is going to stay constant. I'll go with that. But it sounded like you were saying they were not going to move. And that I won't buy.
I'm not sure.
They're gonna evenly space themselves out.
So if I did an even distribution, then they would just stay there? That's what you're going for? Well, all right, well, with no one else saying anything, let's take a look at that. Let's think about the charge, the forces acting on that charge right there. So it's got a force acting down on it from that charge. From that charge, it's got one going this way, from that one it's going that way, and that one's going that way. As close, the farther away we get, the more horizontal these forces go. So those would be the forces coming from what's above it. These forces over here would be forcing it sort of away. What about these charges down here?
It'll be
Uh,
concentrating, pointing up, so they
Okay.
should clump kind of in the corners then to avoid the other electrons, right?
Spirit of it, yes.
Depending on like what the surface you set it on, the earth should start grounding it or start.
Oh, yeah, no, it's isolated, I'm not worried about grounding or any leak of charge. Whatever charge I put there, I'm gonna leave there for right now.
Right, so also because you had your own charge, I'm assuming on it, and when you stepped away, now everything that you are forcing down, it's not gonna, come right back up. It's gonna be all the excess charges that was getting pushed down easily, because it was a conductor, it's not gonna be, pushed back. Same thing with the, experiment with the two foils, when you got the one away from it, everything that was pushed, the negative charges that are pushed down will start rising back up.
It viewed a slightly different scenario. I'm just picturing I got a metal plate here, I add excess charge to it. And because it's a board problem, I can magically have it start out with an even distribution around the edge.
Okay.
Alright, but the other bit that Anna mentioned, these will all be forced upwards. What's gonna be the net force, roughly, what's the direction of the net force? So this will be forced to the corner. Matter of fact, most of these will be forced to the corner, but they can only get so far because the closer they get to these electrons up here that are already in the corner, they're gonna start getting more repulsion going the other way. But you get a higher concentration in the corner. So it starts out with an even distribution, but it will not stay that way if it's a conductor. If it's an insulator, it will, but it's a conductor, it's not. And so what we would end up seeing is a higher concentration of charges in the corners, less so in between,